When archaeologists study objects made by ancient civilizations that they might otherwise know very little about, they would still notice such general trends as the quality of materials going up or down when comparing one historical period to another. Throughout our own lifetimes, we might have seen these changes as well, but then we justify it by saying, yes, we used to make this from metal, but now it's plastic, and that way we're saving expensive materials and energy. We just got more sophisticated and simply don't need as many expensive raw materials anymore to arrive at the same result. Those ancient civilizations would have had their reasons as well, but we still would tend to judge them by the quality of the actual physical objects and not by their justifications, because those have long been forgotten. To put it bluntly, the objects of daily use that all of us buy and own, often shiny and sophisticated when new, do not last that long, do they? And also, how many of those things are imported versus made in the countries where we in the West actually live? The different objects that I'm going to present to you today will serve as representations of actual ruggedness and quality versus only pretending to be those things. So let's see what I have for you today. A local company that obviously makes a lot of chips has dumped a lot of interesting stuff here all at once. Unfortunately, most of it is ripped apart already, and I was only able to salvage a few parts here and there, like some gears or this pneumatic stamping tool here. But on that same pile, we also find this super rugged industrial keyboard and screen assembly from a CNC machine, made by the German company Repair-A-Thon, an excellent find that will serve as an upgrade for my own CNC machine then. We also found two interesting LED lamps, like this work light and this huge Osram LED ceiling lamp here. In this container I also found two linear drives that we will have a look at. And over here someone has ripped apart a dentist chair, and inside that chair we found this big green transformer here. And also two identical potted toroidal transformers that will come in handy later in this episode. Last but certainly not least, an incredible find, an extra large winch so heavy I could hardly carry it away, made in Tulsa, Oklahoma, USA. We have a lot of work to do, so let's head to the workshop then. So whether or not you're an actual Okie from Muskogee, or Tulsa for that matter, I'm sure there are lots of viewers out there who'd find it a nice surprise to have a big item on the bench that didn't come from Germany or even Europe for once, but was made in America a long time ago. It's also not on purpose that after we had 2 winch repairs and modifications in the last Scrapyard Repair-A-Thon, it's always that way. I find one vise and then 13 more. I find one big transformer and then next day I find 15 more. And just like that, we are now in the winch era of this channel apparently. Now, it is hard to understand from the video how large and heavy this thing is. And since the other winches were still set up from the last Scrapyard video, I actually used one winch to hoist another one onto the workbench. If you are interested in that other episode as well, there are 40 or more episodes linked under the video in the video description. Now, the Ramsey Corporation of Tulsa, Oklahoma has made winches for many decades and they are still in business. There are many different models on their website. And since this one doesn't have a nameplate anymore, I can only guess which exact type it is. But it seems to be an extra wide off-road winch in the 24 volt version. Probably a 12,000X or something similar. The motor was apparently made by Prestolite. It also says Wagoner, Oklahoma on here. And it actually looks very similar to a starter motor. Let's assess the damage here though, because there is a lot. The relays were separated and are damaged. The motor has 3 connections plus chassis ground. The 2 upper electrical connections are labeled F. Those are the 2 ends of the field coil. The remaining connection and the chassis ground would connect to the commutator via motor brushes. It is a series wound DC motor. The field coil is not hardwired though. That is done so that you can reverse the polarity of the field coil separately while the polarity at the brushes stays the same. This is necessary to reverse the rotational direction of the motor. This is a DC motor, but it doesn't have permanent magnets. Just reversing the polarity of both field coil and brushes at the same time won't reverse direction. In the end, we're going to use really thick wires here, but for our first test, these thin pieces of copper wire here are enough because the old East German power supply will only deliver 10 amps at 24 volt. I did this not to run the motor properly, but just to see if anything would budge at all. But there is literally nothing happening. In order to test if the motor will spin freely, we have to remove any possible load. So let's remove it from the gearbox. For that, we had to open that gearbox first. Everything is made from very thick and sturdy aluminum castings. Pardon, I meant aluminum, of course, it's from America. Anyway, these Allen screws are all non-metric, of course, and this is one of the rare occasions where I get to use my inch-size Allen screws here. By the way, for all the Germans who have called it Imbus all their lives, the company is actually called Inbus. Mandela effect at work. After peeling off the old gaskets, we find massive steel spur gears submersed in oil, almost like in an automotive transmission. After draining the oil, we can see really nice roller bearings in here, not just mere bushings. To detach the motor, the spur gear has to be pulled off. A Woodruff key connects shaft and gear. Another part that you better don't lose during disassembly, especially since non-metric crescent keys like that are hard to get in these parts. However, with the motor detached, we can try to turn the winch by hand, and it's actually moving quite freely. If the winch didn't really burden the motor, it is probably stuck or completely busted. And indeed, upon pulling the motor apart, we find extreme corrosion, debris and water damage, and the bushing is sitting on the motor shaft like a press fitting. The winch might have been underwater or water was sitting in the motor for a very long time. Be that as it may, Mr. Press the Light from Wagner, Oklahoma, your days are numbered, I'm afraid. Fortunately, I was able to source a replacement motor that will hopefully fit this old winch. But it would take some time for it to arrive, so I continued to disassemble the winch while I waited. There is possibly more to take care of here. Handling the winch with the cable attached makes it much harder to move it around because of the excessive weight that it adds to the winch. So I'm detaching that as well. In the end, it's only fastened with a single, relatively small Allen screw. And since it's really hard to even see smaller problems under that thick layer of grease, grime, dirt, dust and paint from way back when, I wire wheel the entire thing all around and also use degreasers and other methods for a first cleanup. We won't be able to get rid of all the dirt right away though, too many nooks and crannies. And then of course we actually found more damage. A missing plug or bolt, a few broken and bent bolts that we'll have to take care of later. But fortunately we are still able to open the big gearbox as well. Inside we find a steel worm gear working in conjunction with a really beautiful, large and heavy brass wheel. Replacement parts still are available apparently, and that part alone is more than 300 bucks. So after heating them up with a propane torch, I actually managed to unscrew these two broken bolts here as well. We then proceeded by completely disassembling the winch, which wasn't easy because some of the parts were stuck due to corrosion. This, for example, is a lock mechanism, and I'll show you how it's supposed to work once we get rid of the rust. The brass wheel is sliding over these 4 keys here, and it's supposed to be possible to move the axle in an axial motion. This is because of the locking mechanism. There are also 2 brake pads that are being pushed against the drum by 2 springs. We can't forget to reinsert them when reassembling the winch later. Now, pulling the shaft out of the drum of the winch was really hard, when it should actually be super easy and smooth. That's also because of corrosion. And that's why we put the shaft into an acid bath and also applied mechanical methods of rust removal later to take care of that. In the meantime, the replacement motor had arrived. After connecting field and commutator in series for a quick test, I connected it briefly to a small 12-volt battery and it spins up right away. Over the course of a few days, the parts of the lock mechanism have also been sitting in citric acid. They were cleaned, rinsed, dried and oiled and now are in working condition again. The idea is that you can disengage the drum from the rotating shaft by pulling on this handle. But before putting everything back together, it seemed important to get rid of those broken bolts all around the winch. In some cases I could unscrew them after applying heat, but in other cases there was simply no success whatsoever. So I ended up clamping the gearbox casting into the milling machine and started to machine out the bolts. Then I proceeded by recutting the threads with a slightly larger tab. The original tabs are 3/8 of an inch, and this one new thread here is M12. I also just cleaned up the other 3/8 threads with a tab of that size because they looked slightly mangled. Everything had to be put back together in the correct order, which really wasn't that easy at all. Since there are 4 or 5 different gaskets on this thing, I also had to make new gaskets as well. In some cases I went for a special type of silicone to create a new seal, while I also cut out some paper gaskets like I hadn't done in a long time. But I'm not sure they will actually hold all that well. We'll have to see and maybe do that a second time with silicone after a while. So after putting the winch back together and filling the gearbox with oil, I couldn't wait to see her move again. For a first test, I called this battery bank back in action that I had actually built for a solar project some years ago. It would at least be enough for a short test, I thought. The old relays had been heavily damaged at the scrapyard, and there was no way you could reuse them reliably ever again by just bending them back into shape or something. But the only 24-volt relays I had at the shop were these here. They are actually the wrong kind. The original relays have 4 big connections, 1 small one and chassis ground, while these relays here have only 2 big connections and 2 to power the solenoid. The original relays can be used as changer relays, while the ones I have here are just actively closing and that's it. In order to reverse the direction, you need changer relays with 4 connections like these ones. So for the purpose of this video, I always had to rewire the motor between these 2 modes to go spool and unspool. I also attached an ammeter from an old welding machine to the winch. The readings are way off, by the way. The meter shows a much higher current than what is actually flowing. When it shows 80, we're more like at 30 to 50 amps. The winch was then also fastened to my gantry by reusing some of the bolt holes I had drilled for those other winches I tested a few weeks ago. And I additionally strapped this thing down with ratchet straps, just as a safety precaution. In terms of cables and ropes, I had a variety of options to choose from. Maybe the old cable could be reused, or I could use some of these other cables that I have lying around. However, they are super unpractical for the test here in the workshop because they are so long, and that's why I chose to attach this red rope here at first. It should be good for about 700 kilograms of load. The rope also has a steel core, by the way, and should be just right for a test run for this video. But while these small batteries might be enough for a short test run, they quickly drain when discharged with 30, 50 or more amps. So in order to actually power this winch here in the shop, I needed a power supply. So I decided to finally use some other equipment that I had lying around for quite some time here. This is apparently a 1600 or 1800 VA toroidal transformer with 4 24-volt secondaries that I can all use in parallel. I connect them to a 150 amp bridge rectifier module that is sitting on a heatsink. In case that still won't be enough, I paired it with 2 new old stock transformers, 800 VA each, also for 24-volt secondary voltage, and I attached 4 50 amp rectifier bridges to those transformers as well. The transformers were installed into this blue enclosure that we found on the scrap some years ago, and heavy copper wires were used to connect them to the winch. Moment of truth. So, while it is really fun to play around with these things here in the shop, this winch will just have to be installed onto some kind of vehicle. And while I can't do that right now, I tell you I have some fun things planned for you come springtime. In the next step, we're going to take care of a few different things all at once. For that, we're going to reuse the green transformer that we salvaged from that dentist chair, and also we'll try to get that industrial keyboard and screen back in action. And we're going to use all those things to improve the CNC milling machine that I built a few months ago. So maybe you remember anyway, but I built this CNC machine last year. I presented its construction in 2 different videos in 2024 and also showed some first results of the machine in action. However, since it was one of the hardest projects that I ever worked on this channel, a lot of details were still improvised, and it was clear that a lot of those things needed to be improved upon long term. For one thing, some of the motors were still held in place by screw clamps, and I used my DIY mag drill to also, drill more holes into the frame and attach the motors more permanently. The entire way in which the drivers were connected to those stepper motors were also a complete mess, and it looked really shameful. And that's why I've now attached them more permanently and in a more orderly fashion. The wires still need some protective cover though. I also used a very improvised power supply for the CNC machine that I had originally built for a completely different project. Instead of using that, I decided to now reuse the green transformer from the dentist chair to build a new power supply for the CNC machine. And I also decided to install the components of that power supply in a proper enclosure. For that, I chose to reuse the enclosure of this old pump control unit that I also found on the scrap a while ago. With all that being done, a lot of the shortcomings that I mentioned had been dealt with, but one major thing is still a complete mess, and that is how the Arduino and the computer controlling the machine is set up. They need to be installed inside a properly shielded and dust-proof enclosure, just like the one we just found on the scrap, so it's time that we try to get that thing running as well. The first thing that I'm doing here is to separate the keyboard enclosure from the screen temporarily, so that it's easier to move the keyboard around. The enclosures are super heavy. The keyboard is a model KS14271 by the German company InduKey. It comes with an integrated touchpad. I have checked online, and these keyboards alone, even without the enclosure, cost a fortune. Unfortunately, the connector on the end of the cable has been cut off. And since I don't know the pin out of the cable and don't know whether it's PS2 or USB, we'll have to take the enclosure apart. On the bottom side of this enclosure, made by Rittal in Germany, we find a thick aluminum plate held in place by a whole number of screws. And after removing those, we discover heavy aluminum extrusions and a rubber lip protecting the insides from dust and humidity. The backside of the keyboard is additionally shielded with galvanized steel sheets, also held in place by a ton of screws. Under that cover, we find a printed circuit board. The wire connects to it via an 8-pin connector. So let me take a picture here and turn it on its head, and this way you can see as well that the same board was actually used in the PS2 and USB variants of this keyboard. But connector number 2, which would actually lead to a USB cable, is non-existent, and there is no integrated circuit here as well. meaning that this is a PS2 keyboard. However, PS2 only really requires 4 pins. The reason why we have an 8-pin connector though is that we have two PS2 devices here, being the keyboard plus the touchpad, which acts as a substitute for a computer mouse. Unfortunately, the colors of the wires seem to be unambiguous, or at least they don't really mean anything to me. At least I can't know for sure. And since I wasn't able to find a datasheet or pinout for that supposed PS2 controller here as well, I'm really in the dark and can't easily trace the pinout of the connector that way. You know, normally I would look up the pinout of the chip, then use the continuity tester of a multimeter to, trace these pins to the connector. But I can't do that because I don't know what the pins are. And since PS2 devices are not really plug and play, it could take forever to manually find out which permutation is the right one. And while doing that, you could also damage the PS2 controller, ruining the entire project. So I needed some kind of hint here, and my last hope was the touchpad. And as luck would have it, I was able to find the datasheet of that thing. And inside the datasheet, there was this drawing of the pinout of another 8-pin connector, here named connector 3, which is the one connecting touchpad to circuit board. It has 8 rather than 4 pins, because there are 3 additional mouse buttons in addition to the touchpad, while the 8th pin is not used. The 4 connections of the touchpad are directly connected to connector number 2, where the cable is attached. So we now knew 4 of the 8 unknown pins. After that, we could actually have tried to solve this through trial and error. But I simply guessed that if you have 2 PS2 connections in one connector, that you would then simply assign the pins of the second connection in the same order as the first one. In order to test my theory, I took this male-to-male PS2 cable, cut it in half, and soldered it to the wire, in the hopes that it would work. By the way, here you see a picture of the pinout of a female PS2 connector, and I assigned the colors of the wire connecting to the touchpad here, and also the noticeably completely different colors of that stripped apart PS2 connector that you see in the picture here. Drawing pictures like these serves as illustration for my videos, but I also document my own progress in detective work like that in pictures like these. The good thing about that is that you can just look them up in a year or 2 or in 10 years, as if I would remember things like this. Is this kind of detective work any fun though? Well, yes, but only if it really works in the end. But in order to really get this entire unit running, the screen would have to work as well, right? Unfortunately, it was broken though. But since I spent an ungodly amount of time with the keyboard, I couldn't really afford to repair the screen as well while preparing for my trip to Australia. So I simply took another 15-inch screen by that same company, which I got for just a few bucks, and replaced the screen with it. These and other improvements to the big CNC router will be covered in an episode of its own, sooner or later by the way. But was it any fun though? Yes, if it works in the end. Let's have a look at this blue work light then. When I first saw this, I knew that it was something unusual, even though I had never actually heard of the brand before. This company obviously specializes in lamps, cables and other electrical equipment that is supposed to meet demands for heightened safety. And on their website you can find the successor to this particular light we found on the scrap. And while searching for that newer model, I also got lots of search results for lights sold under different names that look very similar to this older model here. And by older, I mean about 2015 or thereabouts. So let's take it apart then, see what's wrong with it and find out if we can still use it for something. It's obvious that this light was built for rugged work environments. The transparent front cover is really hard to take off because it's held in place with this thick and sturdy rubber. Under that cover we find an LED module held in place by a number of screws. And after removing that panel as well, we discover a red circuit board with a converter circuit on it. Most probably it's a rectifier followed by a buck converter or something similar. And here is the most likely cause of why this light was thrown away. This inductor here just fell off the board. Chances are that if we soldered it back onto the PCB, the light would just work again. However, it still wouldn't be very useful to me in particular, and here is why. Just a moment ago, I suggested that this might be a buck converter, while mains powered devices would usually have a flyback converter or another kind of mains power supply. The reason why I said that is that this particular lamp was not designed to be connected to a normal outlet, which is 230 volts AC in this country. Instead, we find 42 volts AC as the input voltage printed onto the PCB. The nameplate on the back of the lamp confirms this, stating that this lamp was indeed built for 42 volts. The purpose of the outlet on the back, which upon closer inspection looks nothing like a normal electrical socket, would be to connect other 42 volt devices to this lamp once it's plugged in. And the nameplate actually provides us with some additional information about the lamp. Just as a disclaimer, I mostly handle equipment that is 40 to 60 years old or older, and I'm not your best source for relevant up-to-date safety information. If this kind of stuff is important to you, I'd suggest you rather buy a book about work safety then. However, I have tried my best to research the meaning of these symbols, and they seem to mean that this lamp was built for rugged environments, can withstand high temperatures, and is dust-proof. And most importantly here for us, it's a class 3 device, meaning that it's supposed to run on a safe extra low voltage, meaning under 50 volts AC or 120 volts DC, and that it's supposed to be electrically isolated from the mains, for example with an isolation transformer. 42 volt equipment is common for work in particularly dangerous environments, like handling electrical equipment inside a water tank. And no, I don't mean when it's completely flooded, of course. But the enclosure has cracks that have been glued over hastily, and the circuit board is falling apart after only 2 years of service. So I'd say you can kiss all that goodbye and forget about all the regulatory mumbo jumbo. Let's see then if the LED panel still works. And since that was printed on the board, we know that it runs on 32 volts. Let's try that by connecting it to a lab power supply. And yes, the LEDs themselves work just fine. So here's the idea that I came up with. I essentially got this thing for free, and I'm not going to spend any money on fixing it. However, the LEDs still work and the enclosure isn't half bad. So I could still use this as a work light here in the shop or outside, particularly if it were battery powered. So here is what I decided to do. I don't have a 32 volt battery, but I can reuse one of these adjustable boost converters that I built in my boost converter episode about a year ago. This one is basically left over from filming that episode. I adjusted it to roughly 30 volts output voltage, obtained from a 12 volt source in this case. Instead of the lab power supply, I can also use this lithium battery here that is left over from a prop making job from a few years back. So I decided to install the boost converter in the place of the old board, and I also attached the battery to the back of the lamp. This way it would be easier to remove it in case I should decide to later use another kind of battery, and this way it's also very easy to recharge. I also soldered a new plug to this used 12 volt power supply so I could power the lamp that way as well, if the battery is drained, for example. And since having this battery and the wire connections out in the open without any protection, it seemed like a good idea to make a detachable cover, which I printed out on the 3D printer. At the moment, all I still need is a strap or lock of some kind to fasten this cover, but I'm already working on that. Another object that we found on the scrap is this huge LED lamp, rated at 200 watts. This kind of lamp is usually used in industrial applications, warehouses or other buildings with very high ceilings. But long story short, this lamp ended up on the scrap for a simple reason: the driver is broken. There is really nothing I can do to repair it though, since the circuit board inside is potted. All you have left is basically a paperweight that would probably also be a nightmare to recycle. Maybe I could use other parts from the scrapyard though to get the lamp back into working order. But for that, let's find out first if the LEDs themselves still work at all. And also what kind of operating point we could use, meaning at what voltage and current will we achieve around 200 watts of power input. As you can see, the LEDs still work. However, my lab power supply doesn't deliver a high enough voltage, and that's why I connected it to the adjustable isolation transformer. The annoying flickering comes from the fact that the LEDs are powered with AC for a moment here. So now that we know that they work in principle, we can try to build a power supply for this lamp reusing the toroidal transformer that we salvaged from that old dentist chair on the scrapyard. Some tests that I performed off camera tell me that we should reach 200 watts at roughly 36 volts DC input voltage. The correct way to drive LEDs is to stabilize the current rather than the voltage, but supplying this LED module with just under 36 volts seems to deliver a stable result. So what I'm basically doing here is to connect one of the 24 volt secondaries of this 440 VA transformer to a classic bridge rectifier, followed by a number of electrolytic capacitors. By the way, one of the biggest disappointments that I've had at one point in my life with LED lamps is that we were all kind of misguided when LED lighting hit the market. I'm old enough to remember the days when fluorescent lamps or even incandescent light bulbs were still the norm. Once the much more expensive LED lamps started to show up in stores, you could always read on the packaging that they would last 10 times longer than the older technologies we had. And you heard stories about LEDs that had been turned on for 10 years straight, yet they still worked. While all that was theoretically true, what they never talked about was the fact that you could build the driver circuits or power supplies of these LEDs in such a cheap manner that they would still break constantly. Here in my shop, I replaced the fluorescent tubes in my 20 ceiling lamps 6 years ago with LEDs, and I have replaced all of them at least 3 times since then. I know and remember that very distinctly because it is very expensive to do that. On the other hand, you might remember that the fluorescent tubes that we found in those East German bunker lamps were made before the Berlin Wall fell, and they still worked. Can you really be angry at me for being disillusioned with this development? So, the circuit board is basically finished, but I also want to use this opportunity to address a common mistake that people make. They want to build a power supply for 24 volts, so they buy a 24 volt transformer, right? Well, actually not, and here's why. The transformer secondary will deliver roughly 24 volts AC, and when you rectify that you will get roughly 24 volts DC. However, that is not a constant but a pulsating direct voltage fluctuating between momentary voltages of 0 and 24 times the square root of 2, which is around 34 volts. If you now start adding electrolytic capacitors of sufficient capacitance to that rectifier bridge, the voltage will rise from 24 volts step by step to almost 34 volts. How much capacitance you need depends on a number of factors, like the size of the electrical load, the internal resistance of the transformer, and so on. You can basically tell when you have reached that point, once adding additional capacitance hardly makes a difference anymore. So once it had turned dark outside, it was awesome to see how powerful this lamp actually is, and maybe I will turn it into some kind of searchlight for the property outside the workshop. Let's have a look at these two linear drives then that we found. The two identical units were made in 1991 and 92 respectively. The label still says made in Western Germany though. They were made by Hanning in Erlinghausen, which is actually in the same part of Germany where I was born and grew up. According to these labels, the motors are also equipped with Hall switches as well. But all wires have been cut off and we'll have to undo that to find out if they still work. In order to make that possible, we have to take the motor apart. This particular type of screw is a bit annoying to remove, but if you loosen the screws a little bit with pliers first, you can then usually just take a normal hex nut to unscrew them. Upon doing that, we can see that we have 3 wires with the same cross-section area attached to the stator. This is clearly an induction motor that is supposed to be run with an external capacitor. This will actually be the case in most applications where motors run directly on mains power. Even if you haven't had much experience with this topic, if the motor doesn't have motor brushes or a commutator, then it's usually an induction motor. And if they are meant to run on single-phase AC rather than 3-phase, they will then usually require a capacitor. There are exceptions like shaded pole motors, but you usually only find those in very small applications, like the fans and microwave ovens. But even if you have identified it as an induction motor for a single phase, there are still different kinds out there. For example, there are motors that are built to rotate in only one direction. They would also usually have 2 windings and 3 connections with one common connection, just like this one. However, one of the windings would only be an auxiliary winding, and that is where you would connect the capacitor, but where you couldn't connect the mains directly. However, this is a linear drive. It needs to be able to move in both directions, to go back and forth again. And that's why I would assume that you have 2 identical windings with one common connection or tap. And that's why you have 3 wires. The nameplate also says that the motor requires a 14 microfarad capacitor. And I have an assortment of motor capacitors of various sizes lying around for this exact purpose. By connecting a variac or adjustable isolation transformer, you can then manually crank up the voltage and check if the motor starts spinning and in which direction. This way I was able to find out which is the common connection and how to move the motor back and forth. It works just fine, and even the bearings still seem to be in good condition. Nothing seems to be wrong with this motor. In the next step, I'm opening the cover of the gearbox, also using an improvised tool this time. Underneath we find the worm gear and some grease, and also a Hall switch assembly consisting of the actual Hall effect switch and a kind of iron sprocket wheel that rotates between a permanent magnet and the actual Hall sensor. The air gap between the permanent magnet and the Hall switch is large enough so that the Hall switch is not triggered unless one of the teeth of the iron wheel moves in between them. The iron tooth shortens the air gap and increases the magnetic field strength of the field lines passing through the Hall sensor, triggering the switch. This is used to determine the rotational angle of the trapezoidal screw and thus the position of the nut that would usually sit on that screw. So I'm soldering new wires to the pins of the Hall switch as well, and luckily enough the good people at Hunning 35 years ago were so friendly as to print the pin out and supply voltage onto the enclosure. However, even with that information I wasn't able to get a signal out of the Hall switches at first, but since I worked a lot with old-fashioned comparators in the past, I had a feeling that this might be an open collector switch, meaning that it needs a pull-up resistor to work. So I connected a 4.7 kilo ohm resistor to the output pin, and there you go. Powering the switch with 5 volts, you could now feed this signal directly into an Arduino or other modern microcontrollers. If you would now add AND switches and a relay, you would have complete control over this 35-year-old piece of technology. Since there is no nut sitting on that screw right now, we still have to find out what kind of screw it is. Being in Germany, it's pretty likely that it's metric. And with an outer diameter of 20 mm and a pitch of 4 mm, it seems likely that this is a metric TR 20x4 trapezoidal screw. These types of nuts are common, but still quite expensive. One much cheaper way to find out if it's actually the size you think it is to print out a nut or parts of a nut on a 3D printer and check if that part fits the screw. Right now I don't have a specific application for these motors. But with all the machines that I'm building here and the constant improvements that I make to my CNC equipment, it's only a matter of time. The important thing here is, you can read all day and watch videos and research any topic on the internet. But in my opinion, tackling practical problems often provides you with a much better learning experience that is much more likely to lead to permanent learning and knowledge. Some would say it's a waste of time to save these motors, but in doing so, you have learned about induction motors, Hall switches, and trapezoidal screws, and have tried various methods of deduction and elimination that you will need many times in the future, whether you are into building or repairing things. If you like the message of this channel and the effort I put into making these videos, I'd appreciate it if you would consider making a donation. A link for that is under the video, or become a supporter on Patreon under patreon.com/tpai. If you can't afford to do any of these things, maybe just give the video a thumbs up. By the way, I'm sorry if the audio quality of this video was a little inconsistent. That happened because it was mostly edited and audio recorded in hotel rooms in Singapore and on the road in Australia, where I just landed. A lot of you guys out there have reached out to me and invited me to places all over Australia, a lot of you even to Tasmania. I would love to see all those places, but unfortunately the time this time around is not enough. I'm only going to be in the Blue Mountains and in the Brisbane area, and I'm already meeting a lot of people there. But if you're still interested, you can still reach out by sending me an email, because I cannot post my phone number or stuff like that publicly. So if you want to make the first step, I will try to reply to you. I'm sorry about everyone else in Victoria, in Tasmania, in Perth, and so many other places that I can't reach this time around. I'm trying to still reply to all of your emails, and I'm sorry that I haven't been able to do that in some cases, but you have seen all the work that I'm doing here. And one more thing, I have a second channel on YouTube that I've had for 10 years or so. I haven't really uploaded it much there at all over the past few years, but I'm now trying to publish some kind of travel blog about this trip to Australia. So there's a link to the second channel in the comments if you're interested in that sort of thing. And see you soon again, reporting from the interesting projects that I'm going to be working on down under.